All right. So I just want to point out that we should all be aware that we're still in the context of solving systems of linear differential equations, right? That's still what we're doing, and it feels like we've been doing it for a while, but it's all about, starting with your two by two matrix, finding the eigenvalues, finding the eigenvectors, and then writing the solution. And if your eigenvalues are both real, it's pretty straightforward. So I'll just point out for a matrix A equal to some generic matrix A, B, C, D, if we find the eigenvalues, if the lambdas are both real, I should just say real, because if one of them is real, they both have to be real. There's no like one real and one imaginary situation here. But if the lambdas are both real, then the solution is relatively straightforward. The solution to the system dx dt equal to your matrix times x is what we've talked about many times. It's x as a vector equal to c1e to the lambda 1t times the first eigenvector plus c2e to the lambda 2t times the second eigenvector. So that's all the context we've been working in. And we also talked last class about how if both eigenvalues are positive, it's an unstable node. If both eigenvalues are negative, it's a stable node. And if one's positive and one's negative, it's a saddle. Which I will repeat again later, but I'm not going to write it down right now. So today we're going to specifically talk about what happens when both eigenvalues are complex or imaginary. And it's a little bit more complicated, not to be punny about it, but we need to kind of back up and say a few things just to make sure that everybody knows how we're going to get this kind of different formula. And for certain, the students in Lee's class, I can almost guarantee he will expect you to do the thing where you find the solution, find the eigenvalues, eigenvectors, do the whole kind of thing. And it's kind of a wonky formula, but it's not too bad once you've done it a few times. So we're going to start with a couple things to just remind everybody. So I'll remind everybody that the square root of -1, we write as the lowercase I for the imaginary constant. Let me do one thing here. Hit my video. And so if we look at other powers of I squared is going to be the square root of -1 squared, which is -1. I cubed is going to be I squared times I, which is -1 times I, which is -I. And I to the fourth, I'm going to think of as I squared times I squared, which is -1 times -1, which is +1. And then after that, you just keep cycling through these same four things. I, -1, -I, 1. So I to the fifth is also going to equal I, because I to the fifth is just I to the fourth times I, which is 1 times I, which is I. And I to the sixth is going to equal -1 because it's I to the fourth times I squared. And I to the fourth isn't really going to do anything because I to the fourth is equal to 1. So that's just equal to I squared, which is -1. And so on and so on and so on. So I to the seventh would be -I to the eighth would be 1, I to the ninth would be I, and so on forever and ever and ever. Why do we care? Well, you'll see. So oh gosh, which class was it? I think in 17A, we briefly talked about finding like the linearization of a function. And there was a little bit more that some of your instructors might have talked about. They might have talked about Taylor polynomials for like the briefest of moments. So a quick reminder, and again, you may not actually need to write this down, but you certainly can if you want to. So I'll just remind you that if I want to find, say, the linearization, that's just a fancy name for the equation of the tangent line of f of x equal to e to the x at x equal to 0, we do the following. Well, I'm going to graph it. Not that we really need that, but here's my graph. And here's the line whose equation I'm trying to find. Well, that point there is 0, 1. And what I really want here is that my linearization L of x should be equal to f of 0, the y coordinate, plus f prime of 0, the slope, times x minus 0, which is x minus the x coordinate. It's just your usual, although written kind of differently, point slope form. Y minus y1, except we brought it over to the other side, equals your slope times x minus x1. And then if we write this down what it actually is, we're going to get here, in this case, the linearization is equal to f of 0, which is 1. F prime of 0 is also 1 times x. Fine, no big deal. Here's the point, though. The point is that if you use a higher degree Taylor polynomial, you get a better approximation of the function. So if I say I want, instead of a linearization, I want a second degree approximation, well, we just add on the next term. So instead of doing just f of 0 plus f prime of 0 times x to the first, our second degree approximation is going to be p2 of x, p for polynomial, 2 for second degree. It's going to be f of 0 plus f prime of 0 times x to the first, plus the second derivative, also evaluated to 0, divided by 2 factorial times x to the second. And we could go on. We can find this. So the nice thing about this example specifically is that since our function is e to the x, every derivative is e to the x, and every derivative evaluated at 0 is just going to be e to the 0, which is 1. So this really nicely becomes 1 plus x plus 1/2 x squared. Just to make sure everyone's on the same page with this factorial thing here, 3 factorial, for example, just means 3 times 2 times 1. Any number factorial just means that number multiplied by all the numbers down to 1. So that would be 6. 4 factorial would be 4 times 3 times 2 times 1, which is 24, etc. Okay, so I'm going to show you one more, and then we're going to say a few more things. If I wanted to find the third degree approximation, it would just be f of 0 plus f prime of 0 times x to the first plus f double prime of 0 over 2 factorial times x to the second plus f triple prime of 0 over 3 factorial times x to the third, which would end up being 1 plus 1 times x plus 1/2 times x squared plus 1 over 3 factorial, which is 6 times x cubed. Okay, here's what I think is cool. And actually, there's a really cool video. I know I posted recently a video about how the eigenvalue, how you can find the eigenvalues a different way somewhere in the modules. That creator, the 3 blue 1 brown website, has lots of cool videos. They have a really cool video about how Taylor polynomials work and kind of how they're really neat. But I'll just show you one kind of neat thing about this, which I think is worth seeing. So what's cool about this is that it actually works if we can pull up this graphing utility. So if I graph e to the x, okay, there it is. The whole point of a Taylor polynomial is that it's a polynomial, which is easy to deal with, right? It's easy to differentiate or anti-differentiate or manipulate in all sorts of ways. And this polynomial, as you add more terms, gets closer and closer to what the actual function is. Let me show you what I mean. So there's the first term. Okay, not very exciting. That's a good approximation right there, but not anywhere else really. But if we add on terms, okay, it's a little better. A little better. And it just keeps going. The more terms you add on, the better, the longer the approximation seems to be valid. And if you do this forever, this function is actually equal to that Taylor polynomial. It's kind of neat. So where am I going with this? Well, we're going to use this to help us with our eigenvalues being imaginary. That's where we're going with this. So I'm going to tell you 2 more Taylor polynomials that are things you can believe. Oh, you can't see what I'm doing. Sorry. 1 second. So just to kind of fill in the rest of that story, the Taylor polynomial for e to the x is kind of the most famous one. There's 3 of them I want you to be aware of. You don't really have to know these. I could totally have skipped this and just told you the formula, but I feel like it's at least good to understand where things are coming from. So e to the x is very generically written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and this goes on and on and on and on, plus x to the n over n factorial, and so on and so forth. And the reason I like to mention this one is because The next two ones I'm going to write down kind of almost look like this if you put them together. Specifically, sine of x is equal to x to the first minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, etc., etc., etc. Every odd power divided by the odd number factorial, and the sign alternates every term. So the next term would be plus x to the ninth over 9 factorial, and so on, and so on, and so on. And in a very, very similar way, cosine of x is equal to all the even powers. So it's going to be 1, which is x to the 0th, which is an even number, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so on and so on. And what's kind of neat, if you have the time, I would really encourage you to graph sine on Desmos and then start plugging in the terms of this Taylor polynomial and see that the more terms you add in, the longer your approximation is good for. Again, it's just kind of neat. So this is all coming down to this. We're going to use these three Taylor polynomials to give us what's called Euler's formula. And yes, it is pronounced Euler, not Euler. I used to think it was pronounced Euler, but then it's like, oh no, it's Euler. So here's what we're going to say. We're going to say that e to the I times theta, where I is just the I we've been talking about, the square root of -1, and theta is some angle, some new number, really. So I'm just going to replace the x here in e to the x with I times theta. This is going to look like 1 plus I times theta plus I times theta quantity squared over 2 factorial plus I theta cubed over 3 factorial, and so on and so on and so on. I'm going to write out a few terms here. Okay, that's probably enough terms. But now we're going to simplify this. So notably, I squared is -1, I to the 4th is +1, I to the 6th is -1, and I is just I squared is -1, so we're going to get minus theta squared over 2 factorial. I cubed is going to be I times I squared, which is negative I, so it's going to be minus I times theta squared cubed over 3 factorial. I to the 4th is 1, so we get plus theta to the 4th over 4 factorial. And then the kind of process repeats. I to the 5th is just I, so we get I times theta to the 5th over 5 factorial. And then I squared is going to be -1, so we get -1 times I to the 4th, which is just 1, times theta to the 6th over 6 factorial. And so on and so on and so on. So if you look at this, I'm going to break up the terms that have i's and the terms that don't. So the terms that don't have any I left over are all the even powers. So we're going to rewrite this as 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, etc., etc., etc. And then the other part is all the things that have i's in them, but we're going to factor out the I. So we're going to write it as I times theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. And the next term I didn't write would have been minus theta to the 7th over 7 factorial. But that's just what sine and cosine are equal to. So this first term here really is just cosine of theta. And this second part over here is really just I times sine of theta. It's a very famous formula. It's kind of neat that it works out this way. So e to the I times theta is equal to cosine of your angle theta plus I times sine of your angle theta. So now, when we try to write our solution as e to the lambda times t times the v1 plus e to the lambda t times v2, the lambda part being imaginary isn't going to jam us up. We're going to be able to say, oh, well, e to the imaginary number times t, you're going to get some cosine plus I sine thing. And we're definitely going to work through that here. See if there's anything else I want to say about this. Nope. I should point out because I'd be terrible not to. Just so everyone can see it, this is probably like the most famous math equation we've all heard of. E to the I times pi equals 0 minus 1. Because your angle is pi, cosine of pi is -1, sine of pi is 0, and -1 can be written as 0 minus 1. And this is really super famous because it's an equation that includes like the 5 most important numbers in math. Big deal. So let's do an example. Let's say we have the following system of equations. Dx dt equal to 4x plus 5y, and dy dt equal to -x plus 2y. And again, normally I wouldn't even write it this way. I just jump straight to writing the matrix. Our matrix here is going to be 4, 5, -1, 2. Now we're going to start by finding the eigenvalues. So to find the eigenvalues, we're going to take the determinant of a minus lambda I. That's going to be the determinant of the matrix 4 minus lambda, 5, -1, 2 minus lambda. We do the usual thing again. You can find the eigenvalues in whatever way you want. I'm partial to just doing it the normalish way, for lack of a better way of saying it. So here's my determinant. It's 4 minus lambda times 2 minus lambda minus 5 times -1. Simplifying, we're going to get lambda squared minus 2 lambda minus 4 lambda is minus 6 lambda. 4 times 2 is 8. -5 times -1 is 5. So simplifying that one step further, we've got lambda squared minus 6 lambda plus 13. And we're going to try and set that equal to 0. And as you're probably aware, it's really hard to find numbers that multiply to 13 and add to -6. There aren't any nice numbers that do that. There are actual numbers that do that. We're going to find them right now using the quadratic formula. So my solution here is going to be, my eigenvalues are going to be lambda equal to, let's see, -b plus or minus the square root of our b squared minus 4 times a times c, all divided by 2 times a. So that ends up simplifying down to, and you definitely want to simplify these, this quadratic formula as much as you can, which is an argument for maybe doing this a different way, because sometimes simplifying the quadratic formula is kind of gnarly. This is going to be 6 plus or minus the square root of 36 minus 52 divided by 2. That's going to be 6 plus or minus the square root of 36 minus 52 is -16 all over 2. And the square root of -16, well, again, it's imaginary, so it's going to be 6 plus or minus, well, the square root of 16 is 4. The square root of -16 is 4 times I. And then finally divide each thing by 2 and get 3 plus or minus 2i. Those are our eigenvalues. And typically we use the one that's plus, like for no good reason other than we have to pick something. So usually we say like lambda 1 is 3 plus 2i, and we really actually don't even care about the other one. We only use one of them really, because technically you're using both of them and it just kind of works out. All right, so now we're going to try and find our eigenvectors. So using the first eigenvalue, our lambda 1 equal to 3 plus 2i. Now we're trying to solve, and you have a choice. You can either try to solve a times v equal to lambda times v, and I guess you could label these as v1, lambda 1 and v1, or if you prefer, a minus lambda 1 times the identity matrix times your eigenvector equal to the 0 vector. Either choice is perfectly reasonable. Which way did I do it here? Which way did I do it? I did it this way. So I'll show you both ways just because I think it's worth seeing both ways, but I do think for eigenvalues that are not nice integers, this second way is the better way to go. If your eigenvalue is nice, I would do it this first way. If your eigenvalue is less nice, I would do it that way. But we're going to see both just to see them. So doing it this way, we're trying to solve our matrix A, which is 4, 5, -1, 2. times our eigenvector that we're trying to find. I'm almost always going to call it xy. I feel like this is where I don't love all the notation stuff. I think Lee likes to call it v1, v2. I'm pretty sure that's what he usually does. Equal to my eigenvalue 3 plus 2i times, again, the eigenvector v1, v2. I really like to use xy though, because well, fine. So doing it this way, we're just going to use one of the equations. Reminder, this matrix equation represents a system of two equations, right? This really is saying 4 times v1 plus 5 times v2 equals 3 plus 2i times v1, and negative 1 times v1 plus 2 times v2 equals 3 plus 2i times v2. We're not going to write that all out because we can see it right there. We only need one of the equations though, and I almost always pick the first one by default. So 4 times v1 plus 5 times v2 equals 3 plus 2i times v1. I would bring all my v's to the right side, my v1s, sorry. So if I subtract 4v1, here's what I've got. 5v2 equals 3 minus 4 is negative 1. The plus 2i is still there, multiplied by v1. And I feel like I've softened on this stance a little bit. This way doesn't seem quite so bad to me the more I do it this way. So if I was going to write my eigenvector, I'm not going to go any further. I'm going to say that my eigenvector is, well, v1 is the coefficient of v2, and v2 is the coefficient of v1. I have to say, doing this for quite a while, that always seems like the easiest way to find your eigenvector. By just not trying to, now I know your instructor probably does something different, and he probably says something like v2 is equal to negative 1 plus 2i divided by 5 times v1. And then he can either say v1 is 1 and v2 is negative 1 plus 2i over 5, or the better choice, in my opinion, is saying v1 is 5 and v2 is this times 5, which is negative 1 plus 2i. But again, I wouldn't do any of that work. I'll remind you, any multiple of an eigenvector is also an eigenvector, except for 0. So if I pick this and you pick this, we're both right. These are both eigenvectors associated with that eigenvalue. And you can even, get much, especially with imaginary numbers, your eigenvector and my eigenvector might look really, really different, because you might have gotten the imaginary part in the first component, I might have gotten the imaginary part in the second component. And seeing that those are multiples of each other is harder to see when imaginary numbers are involved. It's much easier to see that this eigenvector is 2 times that eigenvector. It's a lot harder to see that this eigenvector is 1 plus 2i times that eigenvector. That's a much more complicated multiplication to see. That's an excellent question. Let's find out. And we'll also actually use the actually no, I won't. So if I use the second equation, yeah. So this your question is actually going to expose the thing I just said. So if we use the second equation instead, negative 1 times v1 plus 2 times v2 equal to 3 plus 2i times v2. Now I'm going to bring all my v2s to the right-hand side. So I'm going to have negative 1 times v1 on the left, and 3 minus 2 is 1. So I'm going to have 1 plus 2i times v2 on the right. So doing it the way I like to do it, I'm going to say that my eigenvector this way is, well, v1 is the coefficient of v2, and v2 is the coefficient of v1. So this begs the question, are these different looking eigenvectors multiples of each other? Good question. Well, the easiest way to figure that out is to say, what do I need to multiply by this negative 1 to get negative 1 plus 2i? Well, I need to multiply it by 1 minus 2i. So let's point out, negative 1 times 1 minus 2i is negative 1 plus 2i. Seems legit, right? Okay, so I know that if I multiply this vector by 1 minus 2i, a constant, just an imaginary constant, but still a constant, well, the bottom component will work out just fine. We have to make sure the top component also works out. So if I do 1 plus 2i, the top component, multiplied by my constant 1 minus 2i. Let's see, I get 1 times 1. I get 2i minus 2i, which cancels out. And then I get 2i times negative 2i, which is minus 4 times I squared. But I squared is negative 1, so we get 1 minus 4 times negative 1, or 1 plus 4, which is 5. So yes, these eigenvectors, while not the same, are the same enough. They are multiples of each other. This eigenvector multiplied by the constant 1 minus 2i is exactly equal to that eigenvector. But that just goes to show that if you do this a different way than someone else, your eigenvectors might look very, very distinctly different, even though they're still multiples of each other. So either equation is fine. I always default to the first one. Yeah. Well, so again, I'm not saying they're the same. I'm saying they're multiples of each other. So here's what I just showed. I showed that if I take this one, 1 plus 2i negative 1, if I multiply this eigenvector by the constant 1 minus 2i, I'll get this eigenvector over there. So I'll end up getting the first component being, well, we just said 1 plus 2i times 1 minus 2i is 5, and negative 1 times 1 minus 2i is negative 1 plus 2i. So this eigenvector times this constant gives me this other eigenvector, which really means they're both the same eigenvector, or they point in the same direction. Just the direction's hard to see here because it's complex. Yeah. What else do I want to say here? Yes. Okay, cool. So here's what I would say. To sum up here. For our first eigenvalue, lambda 1, which was 3 plus 2i, our eigenvector ended up being, I'm going to use the one I found first, which was 5, negative 1 plus 2i. And then you never have to do any work to find, you really shouldn't even think about the second eigenvector. Like, I'm not actually going to do it, but I will just point out, you can also very, very easily say that for the second eigenvalue, 3 minus 2i, the second eigenvector, all the imaginary parts just change signs. So you still get a 5 here, you still get a negative 1 here, but instead of plus 2i, you get minus 2i. All right. Here's where things are going to get ugly. Oh, you know what I didn't do? I didn't do it the other way. I said I was going to show you how to find the eigenvalue either way. So you can totally do it this way, which I think is totally fine. More now, I guess. But I said I would probably actually do it this way. So I'll just point out, if we did it that way, here's how things look. So if we instead did a minus lambda I times the eigenvector we're looking for equal to the 0 vector, here's how that math would look. You'd have 4 minus, let's see, my eigenvalue is 3 plus 2i. And then we'd have a 5, and then a negative 1, and then a 2 minus 3 plus 2i times the eigenvector I'm looking for equal to the 0 vector. So now, in this case, if I still use the first equation, I might even simplify this. This is going to look like 1 minus 2i if I distribute that minus sign. And so my equation is going to be 1 minus 2i times v1 plus 5 times v2 equal to 0. And if I bring the v1 stuff to the other side, it's going to be 5v2 equal to negative 1 plus 2i times v1. And then we end up getting the exact same eigenvector, right? My v1 is 5. And my v2 is negative 1 plus 2i. So really, you should just pick a way you prefer to do it. And whichever way seems better to you, you should do it that way. Both ways will work, though. Okay, so we've done all the fun parts. Now we're going to do the gross part. So I would say that there's two ways of doing this next part. And I'm going to show you both. Yeah. So here's the way we typically think of it. We meaning me and Grant. So our solution is going to be, we're really just going to ignore that second eigenvector. In fact, let me check one thing here, just so I'm not saying something totally stupid. Yeah, that's fine. Okay. Yeah. Okay, sure. Sorry, I just want to make there's always this weird little wrinkle here that I kind of forget about. That's fine. Okay, yeah, we're good. So our solution is going to be the following. Our x of t is going to be c e to the lambda t times v, where we're just going to use one of the eigenvalues and one of the eigenvectors. And the reason we do this is because essentially it gives us enough. So in this case, we're going to say it's c e to our lambda is 3 plus 2i times t, and our eigenvector is the 5, -1 plus 2i. All right, so a few things. First, we're going to break up the e to the stuff here. We're going to rewrite this as c times e to the 3t times e to the 2i times t, or I'm actually going to write it as 2t times I. Still times the eigenvector 5, -1 plus 2i. And then the e to the 2t times I thing, that's our e to the I times theta. So we're going to use Euler's formula in there and say, okay, e to the I times theta, where theta is equal to 2 times t, we're going to rewrite that as cosine of theta plus I times sine of theta. So we're going to rewrite this as some constant times e to the 3t times cosine of our angle 2t plus I times sine of our angle 2t. Still times the vector 5, -1 plus 2i. Yeah, I do like doing it this way better. So now here's what we do. We're going to just multiply it out, which I know just. So it gets a little bit messy. So we're going to leave the CE to the 3t out in front. And then we're going to distribute this to each of these terms here. So let's see what we get. We're going to get a vector. It's going to be kind of a giant vector. The first, that's maybe too big. I didn't mean to draw that quite that big. So the first component is going to be all this stuff times 5. So it's going to be 5 times cosine of 2t plus 5 times I times sine of 2t. That one's fine. The next part's a little bit grosser. It's going to be 5 times cosine of 2t and then 5 times I sine of 2t. That's not right. That's a mistake there. I'm multiplying this stuff by the second component there. I don't know why I was multiplying by 5. That's crazy. So apologies there. I made it all big too. Let me just try that again. Sorry about that. Trying to multiply this out the right way. So my first component of my vector is going to be this times 5. So once again, 5 cosine of 2t plus I times 5 sine of 2t. Yes, I wrote the I first this time. Now I'm multiplying this by the second component. So there's going to be some foiling here. So I'm going to have cosine times -1, so negative cosine of 2t. And then cosine times 2i, so 2i cosine of 2t. And then I'm going to have I sine times -1, so minus I sine of 2t. And then finally, I sine times 2i, so plus 2i squared sine of 2t. And then we're going to break it apart into the real parts and the imaginary I parts. So we're going to write this as two vectors added together. So first, the real parts. So in the top component, the real part is 5 cosine of 2t. And the imaginary part is 5 sine of 2t. Don't close that off yet. There's not, I need more room there probably. And in the second component, here's the real parts. The negative cosine of 2t and the -2 times sine of 2t, right? That 2i squared there, that is equal to -2, a real number. Plus, again, the imaginary part in the first component is 5 times sine of 2t. In the second component, it's 2 times cosine of 2t, factoring out the I, and minus I times sine of 2t. And it didn't quite fit. Sorry about that. That's a weird looking vector. I know. Sorry. It's terrible. So we're almost there. So now here's kind of the weird part. We're going to say that c times this vector, there's going to be some constant there, and c times that vector, well, c times an imaginary number is still a constant. So when we distribute this c to both of these terms here, we just get a constant here and a constant there. So we can say that our solution is going to look like x of t equal to e to the 3t times c1 times this first vector, 5 cosine of 2t times negative, sorry, not times, negative cosine of 2t minus 2 sine of 2t, plus c times I is some other constant, c2, same deal. 5 sine of 2t, 2 cosine of 2t minus sine of 2t. And yes, it feels like a lot. And it is kind of a lot. Where does the I go? Excellent question. So this constant here, that is whatever that constant was times I. I is a constant. It's weird, right? It's square root of -1, but it's still a thing that never changes, right? That's all it means to be a constant, is you don't ever change. I is I, right? It is what it is. Sounds like I'm talking about myself. I is I. So if you multiply that I by some other constant, which could be real or imaginary, who knows? We didn't say what C was. This times that is still a constant. I just gave it a new name. And I'm kind of trying to, in some ways, obscure the fact that it might be imaginary or real. We don't really care. Yeah. Yeah, but the more general format is to write it as C1 and C2. You're not wrong, but we write it this way because that's how we usually write it. So that's our general solution. And then if they gave us initial conditions, say we were told that at time equals 0, did I use x's or y? Let's see, let me go way back. I used x and y. X of 0 is equal to 3 and y of 0 is equal to -2. Then we can plug those in to find our C1 and C2. So plugging in 0 for t, 3 for x, and -3 for y, we're going to have that 3 -2 is equal to, okay, we're going to be real careful here. On the right-hand side, e to the 0 is 1, so I'm not going to write it. I get C1 times cosine of 0 is 1, so I get 5 there. And in the bottom part, I get -1 minus 0, because cosine of 0 is 1 and sine of 0 is 0. It's probably important to remember that if you're trying to find constants here. Cosine of 0 is always 1, sine of 0 is always 0. So the bottom point there is going to be -1 plus C2 times 5 sine of 0 is 0, and I get 2 cosine of 0 minus sine of 0. All right. I've mentioned before how if your initial conditions leave you with a 0 in one of these spots, the system is pretty straightforward to solve. Specifically, I know in my first equation here that 3 has to equal C1 times 5. So C1 had better be 3 divided by 5. I have no other choice. And then in my second equation, I have -2 equal to C1, which is 3/5, times -1 plus C2 times 2. So then I can solve for C2 and get, let's see, -2 plus 3/5. So I've got -10/5 plus 3/5 equals 2 times C2. So -7/5 divided by 2 is going to be negative 7/10. So negative 7/10 is equal to C2. So our particular solution here, which I really, really don't want to write out, but I guess I will, if I can fit it in here. Our particular solution is that x of t is equal to e to the 3t times 3/5 times the vector 5 cosine of 2t minus cosine of 2t minus 2 sine of 2t plus c2, which is negative 7/10, times the second vector, which is 5 sine of 2t, 2 cosine of 2t minus sine of 2t. Oh, that's terrible. Sorry, it's very scrunched in there. So I will say, I do think Instructor Lee does one really smart thing here. He doesn't write these a million times. He calls them like G and H and then just does that, which is kind of a better way to go. So I will say this way of doing it, I feel like is easier to approach in that you're really just writing down the things we know, and then yeah, you're doing some terrible multiplication. And it is kind of terrible multiplication, but it's very doable as long as you are careful about keeping track of what's what. I'm trying to see if there's, okay, yeah. I can't really do another example yet, definitely not. So here's what I want you to see. So I'm actually going to write this out again, but I'm going to write it out as my solution. So my solution here, the top row is that x of t, not as a vector, just the component x, is equal to e to the 3t times 3/5 times 5 cosine of 2t. I guess the 3/5 times 5 is going to give me a 3. So it's e to the 3t times 3 cosine of 2t plus e to the 3t times negative 7/10 times 5 sine of t. So it's, I guess I could, sure, I can factor out the e to the 3t part and say I've got negative 7/10 times 5 is negative 7/2 sine of 2t. And in a similar way, although more complicated, the y component, the second part of my solution, is going to be e to the 3t times 3/5 times all that. So it's 3/5 times negative cosine of 2t minus 2 sine of 2t plus negative 7/10 times 2 cosine of 2t minus sine of 2t. Which again, I know is terrible to write. But what I want you to see, and I do think I'd be better off just graphing it, is what this looks like. So why this gives us a different equilibrium type than we've seen so far. This isn't going to be a node or a saddle because of the following behavior. So let's go back over here and look at Desmos for a moment. So if we were to graph both of those, even though they're kind of terrible, here's what they look like. So if we have, sure, I guess I've already used that. So if we graph it as e to the 3, I'll use x instead. Pretend like x is t times 3 cosine of 2x minus 7/2 sine of 2x. Let's turn this other one off here. So look what happens. As time increases, you get this oscillating behavior, right? And if you zoom out a bit, I know it looked at, right? I mean, things are getting very, very big very fast because right? So you might think those are vertical asymptotes. They are not. It's just that things are so large that it's hard to see the top of that. But really, we're getting, let's see if we go a little further here. No, oh, I turned it off instead of zooming out. Sorry. Can we even see that really? Yeah, it's a little bit, it's kind of, so like it looks a little bit crazy. But what's really happening there is as time increases, the x values get negative, and then once sine and cosine turn back to being positive, you get really, really positive things, all the while still increasing in the way that e is increasing. So we've got something like, if we graph this, if we plug in 0, we're starting at 3. So our x of t starts at 0, 3, and then oscillates like that. getting bigger and bigger. And oh, sorry. Yeah, thanks. Yeah, he drew something like that. That's what x of t is doing. And y of t is doing something similar. If you plug in 0 for t, you're going to get, well, the initial condition, which was -2. So the y one is going to start there at 0, comma -2, and then also do this oscillating thing. Or it probably goes down a little bit first, but then does something like that. So they're both getting bigger and bigger and bigger, but not always in the same direction. So that means they're going to spiral outwards because they're going to keep moving away from the origin, but they're going to be really, really negative and then really, really positive and then more negative and then more positive. They keep going around and around and around. And if you use one of the graphing tools like, where'd you go here? Not Desmos, but the other one, where'd you go? So you can see this if you look at, sorry, that's the one I want. Yeah. Yes. So if you throw that initial equation, which was, where'd you go? It's way back here. Yes, you can definitely ask earlier too. I just sometimes get carried away with the math, forget about the attendance sheet. But if you look at this last part here, sorry, where's my matrix I started off with? So if we look at 4 times x plus 5 times y, and then the next one is -x plus 2 times y, and we graph it. Oh yeah, it's looking pretty spirally. Although this one actually doesn't look super spirally, I gotta say. This one is not showing the spiraliness very well, in my opinion. Some of them are better at kind of seeing how spirally they are. Other ones are not super spirally looking from the get-go. Let me actually check one thing here. No, it's the same. Okay. So yeah. So even though it doesn't look super spirally, it is a spiral. You just kind of have to go out further along to see it kind of start to make that turn. So that's how you find the solution to one of these that has imaginary eigenvalues and eigenvectors. On Friday, we'll talk more about this, but we'll say kind of look at the other way of doing it, which feels like it's a little bit less straightforward, but the writing down of things is easier. So we'll do it that way as well, just to kind of compare them, and then you get to pick which way you want to do it. All right, that's all I got. Make sure you get your name on the attendance sheet. Sorry for waiting till the last minute to hand it out. I did not mean to. I always feel like this one doesn't look spirally enough. It bothers me. Hmm. It's frustrating. I want it to look more spirally. Oh well. Close church. Yes. Yes, of course. You're welcome.